All right, we're going to get started now. Hi, everyone. Welcome to Twitter. I'm David Helder. I'm part of the messaging pub sub team, and I work here with CJ. I just have a few logistical things to cover, and then I'm going to hand it over to Flavio, who's going to be sort of the MC tonight. First of all, most important thing, Wi-Fi. If you haven't seen the signs, they're around you. The Wi-Fi network is named Cuckoo, and the password is Redbird Pounce Flag. The second most important thing, bathrooms. Bathrooms are outside and to the left? I don't know, left or right, but you go through those other double doors and the bathrooms are, you'll find them around there somewhere and someone will stop you if you go the wrong way. And then finally, could you quickly stand up if you work at Twitter? Or raise your hand if you're at the side. Okay, oh great. So there's a bunch of Twitter people here. If you have any questions about Twitter or working at Twitter, talk to those people. We are hiring, so come talk to us. Or just if you just want to talk about like what it's like to work at Twitter, we're happy to talk about that too. And with that, I will hand it over to Flavio from Confluent, who's right there.
Thanks, David. Hello, everyone. I'm Flavio. I work for Confluent, who turns out to also be hiring, if you're interested. And so I'm very pleased to be here today with these great talks about both Apache Bookkeeper and Apache Kafka. The common topic is messaging, as the title of the meetup says. One of the interesting things about the two systems and all the applications that have been built around them is the fact that they rely on this abstraction of logs. Both Kafka and Bookkeeper had to work hard to implement that distributed, reliable log abstraction. And today we'll be seeing a bit about the experience that those folks at Yahoo, Twitter, and Confluent/LinkedIn had to go through to implement these great systems. So I'm not a speaker, so I don't want to take too much of the time. We will start with CJ Gould from Twitter. Where are you? CJ is over there. CJ is the tech lead for Bookkeeper and distributed log here at Yahoo, and turns out to be the PMC chair for Apache Bookkeeper as well. So CJ, please.
Okay, so I will just start. Sorry. Sorry. Okay, so as what Flavio mentioned is about log. So log. Oh, sorry, I don't think it's okay. So log is probably the most well-known data structure. It's everywhere in every engineer's daily life. It's an append-only, totally ordered sequence of record. We have been used log to address a lot of challenging problems at distributed systems at Twitter, and I'll just start with an example on how we use log to implement compare set on Manhattan, which is our eventual database, eventual consistent database. Sorry. And so this is a simple abstraction on how Manhattan looks like. It complies with three components: client, coordinator, and replica. And so the client sends a request to coordinator, and coordinator will figure out what replicas to write to. And each request will be assigned with a timestamp when they write to the replicas. And replica would use timestamp to decide which change would win on updating the data. So it's a very simple model on eventual consistent database. But when we want to implement compare instead, it encounters a problem. What kind of problem we encounter on implementing compare instead? It's conflict. What does conflict mean? So for this example, there are two cache requests on updating same key X to different value. And so for the first cache request, it tries to update the value 3 to 4. And it succeeds on first replica. And the second cache request, it tries to update the value from 3 to 5. It succeeds on the third replica. But when the first request try to update on the third replica, it will find the value has already been changed to 5, and it will fail. And same apply for the second cache request. So this is the conflict. It means we don't know what a value would be changed to. It would be 4 or 5. And even worse is our replica has been changed to a different value, and the system couldn't recover after that. So there's no eventual consistency you can achieve on this model. So what we can do is a common pattern to address these issues to use a log, which sequence all the updates into database. So the data flow became coordinator write the request into a log, and all replica read the log and apply those changes in order. So in this case, the first request, cache X from 3 to 4 will come first. It updates all the value to 4. And so the second cache request will just fail because all the replicas state has been changed to 4. And it guarantees all the data are consistent across all replicas. And this is a very common pattern on addressing distributed systems, which is called PubSub. And log is the foundation of PubSub. And because this pattern is so common, which it makes us thinking if we can build a log as a service, which can benefit all the distributed system that could use this pattern to address the issues. So when thinking about building a log service, we need to first figure out what kind of requirements we want to meet and what kind of challenging problem we want to address. So the foundation of a log service should be durable. Why durable is important? Because we need data to be persistent on disk before acknowledge, so there's no data loss when machine crashes. And durable in a single machine is not enough. We also need data to be replicated across multiple machines to improve availability. And because the data is replicated across multiple machines, we need to make sure all the data are consistent across replicas. Otherwise, if different readers seeing different value, it will just screw up all the service built on top of this log service. And to clarify a bit why these three properties are so important to us, because we have been operate several services that don't support strong durability for years, and they are running very well. They either rely on periodical flash or you rely on file system to do flash in the background. They are running very well in most of the time, but when crash happens, we lost data. We have been asked by customers how we can quantify the data loss, and it's so painful and it add a lot of operation overhead to our team. So when we start thinking about building a log service, we need to make sure the foundation is durable, replicate, and consistent. And we should be able to support different type of workloads, and those kind of different workloads built on top of this log service should be able to tune their latency to meet their requirements. So when we build the foundation of a durable, consistent log service, we need it to support high performance, achieve low latency, and support high throughput. And it should be able to scale when the service built on top of it scaled. And this system should be easy to operate and simple to integrate, because log is a very simple abstraction. It should not make the users using a log service much complicated. And to clarify a bit what does low latency and high throughput means in a log service, we need to first thinking about what kind of workloads in the log service. There are three typical workloads in a log service: writes tailing reads in catch-up reads. And writes append the data to the tail of log, and tailing reads would just read the tail of log. And catch-up reads are reading from early point of log. Catch-up reads is pretty common pattern in the log service, such as if you want to bootstrap a new service, you probably need to read all data to build a new state. Like in database, if you want to bootstrap a new replica, you also need to read from log, very early point of the log. So in the log service, writes in tailing reads care about latency. It matters on how fast messaging flows through the system. And the catch-up read cares about throughput, which means it matters if it is able to catch up with the latest data. If it's unable to catch up with the latest data, it will just fall behind forever. And so in most of the system, ideally there would only have two workloads, which is writes in tailing reads, because people would just keep tailing reads. And most of the existing system operate very well on writes in tailing reads. But in reality, from our experience on operating existing systems, catch-up reads plays a very critical role on break the system. So when we're building a log service, we need to make sure these three typical workloads could be isolated from each other. The catch-up reads should not affect latency-sensitive workloads like writes in tailing reads. So isolation became a very key component on building a log service. And we have been looked around several systems and decided to use Bookkeeper as a foundation because of its three nice properties. First, I/O isolation, parallel replication, and its easy understanding consistency protocol. So Bookkeeper is kind of well designed to meet the workloads in the log service. So the writes are appended into a general log and group commit to the general disk. And after they are persisted on disk, they will be put in the memory table to serving all the tailing reads. And the data in the memory table would just be flushed asynchronously onto index disk in ledger disk. They would be used for catch-up reads. As you can see here, all these three typical workloads are kind of isolated to be served by different I/O components. It gets us to pretty low latency and also high throughput. And it also does pretty well on I/O isolations. And in Bookkeeper, the data are kind of parallelly replicated by writers. It reduced the add latency would be introduced in other replication scheme like master-slave replication. And with column X mechanism, it is able to mask any slowness and failures in the write pipeline. It gets us to a pretty good low latency on write side. And on the read side, it used a mechanism called speculative read, which it will retry will send a speculative read to other replica when it didn't receive a response from the first replica. It gets us to very predictable low latency on read pipeline. And all the speculative reads is kind of a benefit from Bookkeeper's easy understanding consistent model. And how does the consistency model looks like? So the writer would just keep adding entries, and each entry would be assigned with an auto increment entry ID. And with acknowledge coming back from bookies, the writers would advance a pointer called last add confirm. The last add confirm here is kind of a boundary of consistency, which it means all the data 8 before last 8 confirm are already persistent, durable, and acknowledged by writer. And the reader can just read any data before last 8 confirm. It couldn't read beyond last 8 confirm, which it helped us to get the consistency across readers. And on the right side, Bookkeeper doesn't enforce any strong leader election. It focuses on the storage itself and provides a built-in mechanism called fencing. What fencing does is it tries to prevent the old writer writing to the same log when there's any leadership change or failover. It achieves the consistency across writers. And the nice property here is, as you can see, there's not strong coordination between writers and readers in order to achieve consistency. So it gets us to scale the readers independently of scaling the writers, which we can get a pretty high throughput. Yeah, so Bookkeeper is kind of a very cool storage for log service. It addresses our top 3 concerns about log service, which is durability and replication and consistency. So is it enough? Then we can call it a day? Not actually, because Bookkeeper's API is pretty low level, because you need to manage the life cycle of ledgers. In a large organization like Twitter, we'd like people to think in terms of name log and using a more stream-oriented interface to model their problem in a way like only write to an log and read from the log. We don't need people to think about the problem in a set of numbered ledgers and manage the life cycle of ledgers by themselves. And in a large organization, we want to organize those logs together into namespace for easy management and also for reusable for different organizations. And so to leverage Bookkeeper, a name log is kind of breakdown into log segments based on size or time. And it helps us to break down the data to equal-sized log segments, which those log segments could be spread across the cluster and help balancing all the data distribution and also prevent any hotspots. And because the data is keep appending into a log, we need to provide a way to delete all data in the log. And for most of workloads like replicate state machines, they need to control how they consume the data before they delete all data. So we need to provide explicit truncation. And for other workloads like analytic workloads, they probably don't care about the old data. So we just provide a very simple time-based exploration. So people doesn't need to care about if I forgot to delete the old data. And besides these basic concepts, as we mentioned, we want to build a foundation that can support different type of workloads from transactional database to offline analytics. We should be able to tune the data pipeline to support to meet the different requirements from different workloads. So this is how the data pipeline looks like in distributed log. So on the right side, writer will write a data called log record, and those log records would be first buffer into an output buffer. They either flush immediately or flush periodically or when the buffer is full. So different type of workloads can trade the latency for throughput to meet their requirements. And on the reader side, reader use a mechanism called read ahead, which is proactively pulling the data from bookies and make them available for reader to consume. And to even reduce the latency on polling, we add a mechanism in Bookkeeper called long poll, which can be more efficient to read the data from bookies. And it reduces the latency on the whole data pipeline. So with the name log and log segmentation, log retention, and tunable data pipeline, it's the core of distributed log. But we are not done yet because our goal is to building a log service. So in order to build a log service, we first add a serving tier on top of distributed log, which calls on the right side, which called write proxy. It accepts finding writes from multiple sources, and it manages all the owners or all the ownership of logs in fail over the writers when there's any failures happens. And to point out here is we use ownership tracking here instead of leader election, because as we mentioned before, in the distributed log core, or like the foundation of Bookkeeper, it already provides a built-in fencing mechanism. We don't actually need a strong leader election. We can just build it. We can just build a simple ownership tracking mechanism to help clients figure out what proxy own which log, and when there's any failure happens, it would just fail to any other proxies. So it's purely a steady service. On the read side, we add a serving tier called read proxy. What read proxy does is it catches the data, and once it catches the data, it could serve a large number of readers, so we can scale the read traffic independently of scaling writers. And to point out here is all the write proxies in read proxies are kind of steady. They are not tied with any data or state. So they can optimize on running in a multi-tenant data center environment, such as Twitter's Meso scheduler, or they can running on any cloud service like Amazon EC2, because they are purely steady. So even cooler is the whole software architecture. It's kind of layered. So we don't even need, there's no like spatial law on each individual software stack. So we don't even, the same software stack can be run in multiple data center without changing any line of code to achieve consistency across multiple data center. All what we need to do is adding additional data placement policy, which is kind of customized Bookkeeper's data placement policy. And the data placement policy needs to do is to be aware of which data center the bookies are in, and then need to make sure we allocate the bookies across multiple data center and ensure the acknowledge from majority of data centers. So it's the same stack that can running within a local data center, and it could running across span over multiple data center and achieve global consistency. So this is the whole stuff that we build in distributed log. It provides the core features that we think they are good enough to support different type of workloads. And we leave the other stuff like how to partition the data, how to route the traffic, and how to tracking the offset for the readers to the application. Because on different type of application would have different type of requirements in terms of latency, consistency, and durability. They can tune all these parameters once the foundation is consistent and durable. And I'll just give you an idea on what kind of application that we have been running on distributed log. So distributed log is kind of start around 2012, and it's on production on 2013. it has been used on several applications in Twitter. It serves different type of workloads, from transactional database to offline analytics or general purpose of PubSub. And the other system to point out is like reliable cloud data center replication and search ingestion are kind of replicate state machine workloads. So they are kind of different from, a bit different from general purpose of PubSub. And we also have a system called Durable Deferred RPC system, which is also using distributed log as the foundation. And this is a rough idea about how many logs we support at Twitter. So right now the data is kind of, we have 20K logs that are live. And those logs are kind of comprised with 630K log segments. And we are moving more and more application onto this platform. And because with the storage in serving tier, with a layered architecture with storage in serving tier, we can scale this independently. And those data are kind of, we support different retentions from days up to year. And I'll just give you a simple example on how efficient on finding in, find out. So on right side, the right proxy kind of accept 250 megabytes per second, and the replication vector is 3. So it is supposed to have 750 megabytes writing to Bookkeeper, but with the batching and the compression on the right proxy, Bookkeeper only receive around 400 megabytes here. It's kind of reduced a lot of, a huge amount of bandwidth to Bookkeeper. And to point out here is the compression is not high. Is we kind of trading the latency for throughput. So if we want to achieve much higher compression, we can increasing the grouping mechanism to even better compression. And on the read side, as you can see, the Bookkeeper is totally serving 450 megabytes. But on the read proxy side, you can see we are able to serve around 25 gigabytes per second, which is a huge amount of difference between bandwidth. That is because of which are the benefits of the caching on read proxy, and which we are able to scale the serving tier, which kind of network bound from scaling storage, which is kind of disk IO bound. No, this is sequence. This is aggregate number. This is how it's a application example on how the traffic looks like in the application. This is a graph is kind of showing how we are able to tune latency for different type of workloads. At the bottom is kind of a transactional database workload. On top is kind of the general purpose PubSub. So we are able to tune latency for different type of workloads and meet different requirements. And it's all running on same software stack. And so thanks everybody in the team to build distributed log, and especially thanks to Robin, who was the tech lead the team to build the layered architecture. And we think such layered architecture is good for both large organizations that have multi-tenant data center environment like Meso, and they are also good for smaller startups that are using Amazon EC2. They should be able to run the same stack to meet different type of requirements. And all the changes, all the improvements we made in Bookkeeper to reduce the latency, improve the performance are kind of available in Twitter's branch. And Lee and me and our some of members in our team tried to merge those changes back to the community, so it will be available for everyone. And we are looking forward to open source distribute log. And yeah, this is the Q&A. No, okay, so the question is the replication across data center is open sourced? So as I mentioned before, so as you see here, there's nothing special. The replication across data center here is we just customize data placement policy, which to give you a background is the data placement in Bookkeeper. It's an interface. You can custom whatever data placement you want. And within Twitter, we provide rec-aware data placement policy. And we also have a region-aware data placement policy. But it's kind of, you need to align the data placement policy with your infrastructure because different type of network topology would be used in different type of companies. But it's simple, and we already push our region-aware data placement policy to our branch. So you can check out as an example. So the question is comparison with Kafka. And so when we start a project on 2012, there's no durability and replication on 0.7. So, and it's available on Bookkeeper. So that's why we start the project with Bookkeeper. And besides that, we think in order to support large number of the logs in for different type of workloads, Bookkeeper has a better architecture in terms of I/O. And because most of the time, file systems do very well for tailing reads in writes, but when there was a problem, when there's any catch-up reads, it would start reading a lot of old data from file system, and it would affect the latest data from patch cache. So it's kind of a pain point. And also with durability, if you want to do async, it would be better to have a single channel that commit all the changes. But I think things has been getting much better on Kafka side. And if you want to know more about Kafka, you should hear from Neha. Yes. 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 Okay, so it's here. Oh, sorry. So suppose if it fails in the it failed on writing the third book key, and there was a mechanism called auto recovery in Bookkeeper, which is kind of a daemon that can run separately with Bookkeeper, or you can run within a Bookkeeper. It would check which bookie are kind of missing data. They will backfill all the data from the other bookies. And on the reader side, because all the entry are kind of assigned with an entry ID, so it's easy to do when there's a missing on the bookie side, you could try on a different replica. So it's fair. And it's predictable. Yep. Any other questions? Okay. Yeah.
All right. Our next speaker is Neha Narkede. So Neha is the head of engineering, co-founder at Confluent. She turns out to be my boss as well. And in her spare time, when she's not being head of engineering or co-founder, she is PMC and committer of Apache Kafka, and she's probably the best person in this room to respond to Kafka questions. So we had at least one. So Neha.
Okay. Of course. No, which is good. Okay, let's get started. Can everyone hear me? Okay. Hi, everyone. I'm Neha Narkide. Thanks for the great introduction, Flavio. As Flavio mentioned, I'm co-founder at Confluent. Prior to that, I led Streams infrastructure at LinkedIn, where I was responsible for LinkedIn's Kafka and Samza development and deployment. And for the longest time, I've been involved in Kafka since we started that project at LinkedIn. In my 5 years of working on Kafka, I've seen Kafka adoption grow from 0 to now more than 1 trillion messages per day at LinkedIn and at several other companies worldwide. So in this talk, I'm going to walk you through kind of our Kafka story at LinkedIn, how we re-architected LinkedIn's fragile data infrastructure to a much more scalable and real-time stream data platform, and how several other companies, including LinkedIn, use Kafka in production. When I joined in LinkedIn, this was back in 2009, I was working on the search team. And in my spare time, I dabbled in other data infrastructure systems and got involved in the Who Viewed My Profile product. And I noticed that the way data got into the search systems was very different from the way, data got generated for serving Who Viewed My Profile results. So I got involved in, digging through how data flows through all the various systems at LinkedIn, and it turned out that we actually had millions of little data pipeline between every new data system and every new data source that we wanted to collect at LinkedIn. So let me give you a few examples. Like with every website, we had a couple relational databases back then and a set of scripts for loading relational database data into the warehouse. At that time, we started adopting Hadoop at the same time. And so we had a different set of scripts for loading data into Hadoop, which happened to be at that time through fragile CSV dumps. And we have the third way of loading the same data into all the different caches, which was through a different tool we load back at LinkedIn called Databus. Okay, that was just the relational database changes. We also started adopting NoSQL stores pretty rapidly. And since the previous set of scripts were only good for relational databases, we wrote different set of scripts for our NoSQL data stores to pull data in and out of Hadoop. Now, data in databases is really resident data, but a lot of useful data, like you may know, is to do with finding out what happened. And this is especially true for relevance, where you want to find out how users are using your products in order to build better products. Back then, our pipeline for collecting this sort of activity data was pretty ad hoc too. Activity data kind of got logged into these minute or hourly files on all our front-end machines, and we had a couple of scripts to actually rsync that data over into Hadoop, and a separate set of scripts to do the same for our warehouse. Our real-time use cases were built on top of ActiveMQ back then. And, because these legacy messaging systems are not very scalable, with every major use case, we spun up, a separate cluster. In short, this was pretty operationally expensive. Then we had a separate pipeline for loading all our application logs into Splunk for searchability, a separate pipeline for loading these metrics into our company-wide monitoring application. And pretty soon, this was what our data pipeline actually looked like. Now, if you focus on any one part of the picture, all the connections make sense. But if you look at sort of the broader access, broader picture of the data, any kind of access to a lot of data sources was a big pain. The problem was that data was very fragmented. For example, our business activity data was available in the warehouse, but not in the company-wide monitoring system. So there was a way to get, analytical sort of once-a-day information on business metrics, but no way to do real-time alerting. On the other hand, we had our application metrics in the company-wide monitoring system, but not in Hadoop. So there was no way to do sort of, analytical questions like what are the top applications with the largest latencies slowing down LinkedIn. In short, the real problem we had was lack of agility. Making changes to any one part of this pipeline broke many other parts of the same pipeline. In short, this was pretty much a giant mess. So we took a step back, and we thought hard about the problem. Definitely adding these point-to-point connections between every new data source and system that we were adopting at LinkedIn wasn't a very great long-term solution. In fact, what we envisioned was this sort of a string data platform where new data sources got registered and any system that needed access to a data source could simply plug in and subscribe and get a stream. And if we thought if we did this, then there would exist a very rich ecosystem of applications around it that could just subscribe to these streams of data and build meaningful things from it. So, the heart of this vision, really, the real problem that we were trying to solve is really what I'm going to refer to as data integration. It might have other names elsewhere, but the problem is really just making sure that data ends up in all the right places eventually. Okay, so being infrastructure engineers, we thought that there has to be an infrastructure solution to this problem. It is actually much more than duct taping a bunch of tools together. And we thought that, well, this problem isn't new. Messaging systems have existed for a very long time to move data around. And so that's where we started. We started hacking on these messaging systems, and we had ActiveMQ in some part of the website. We played around with RabbitMQ. And it turned out that these messaging systems had a bunch of problems. First, throughput requirement for any of these large volume data sources like logs turned out to be extremely expensive on these messaging systems. Second, the integration with batch systems like Hadoop just wasn't what most of these systems were designed for. In fact, integration with batch systems requires the ability to maintain these large, backlogs of unconsumed data. And messaging systems, in fact, these legacy messaging systems just get slower and slower as the amount of unconsumed data accumulates over time. And these were mostly, merely a result of persistence, not being taken very seriously in these systems. It is very much of an afterthought, an option you can turn on, not something that is supposed to be on by default for high performance. And most importantly, we actually wanted to be in a state where we could do the stream processing on all our data. And to be able to do stream processing, you need the ability to rewind and reprocess data. But these messaging systems, they delete data the moment subscribers have subscribed to it. So they aren't really, designed for any kind of reprocessing. And lastly, we actually needed ordering guarantees, especially in the presence of sharding. So sharding, so you can horizontally, scale your data, and ordering, because imagine if you wanted to publish sort of profile updates to your search index. You don't want a latter update for the same user to precede the previous one. So ordering is extremely important. So as we went through, these problems, we found ourselves wanting to re-architect these systems. So we just started from scratch, and that is what led to Kafka. At a high level, Kafka is a distributed pub-sub messaging system. You have producers that send messages or events or data to a central cluster of brokers. And you have consumers that subscribe to categories of data or topics to get access to all that data. Now, Kafka is very different from a couple of other messaging systems in a number of different ways. First, it is distributed from the grounds up, so every stage of this system is fully distributed, lives on multiple machines. Data is persisted, so data is persisted by default in these write-ahead logs, and it is fully replicated across a configurable number of brokers, so replication is built in. And it is multiple subscriber system. So you can have either 0 people consuming a feed or n people consuming a feed. The advantage of Kafka is that adding subscribers for the same topic or log, as CG mentioned, is very easy and it's scalable. The central abstraction that Kafka provides is a log. And it is worth talking a little bit about it, though CG touched upon this abstraction in his talk too. Log is nothing but an abstract data structure that has a couple properties. It is sort of like a structured array or a feed of messages. So data is completely ordered. Data is append only and hence immutable. So once data is written, it doesn't change. And events or records are ordered by time. And every record is addressable using a unique index. This is sometimes known as the log sequence number, or in Kafka, we just call it an offset. Now, each record in this log is written using some serialization format. I won't get into the details of that, but Kafka is essentially serialization format agnostic. You can assume that this is just a byte array. So that is the, logical view of the log. You might think, this log abstraction is cool, but how does it help build a messaging system? It turns out that actually logs are a fantastic abstraction for building messaging systems. Here I've shown the same view of the log, and now there is a source system that appends new writes to the end of the log. And there are 2 destination systems, system A and system B. Now notice that in spite of having 2 different subscribers, there is only 1 log, so we're not maintaining a queue per reader. And a really nice side effect of that is that both the subscribers see the data in the same order, which is dictated by the log. Most importantly, log, this log sequence number, it applies the notion of time to the log. Now when I say time, I don't mean physical time, like it's 7 p.m., but really logical time. So, for instance, if system A has subscribed up to record 6, then it is at time 6 in the log. And if system B has consumed up to record 2, then it is at time 2 in the log. And this ends up being really important because now you can reason about the state of system A and the state of system B based on how much of the log they have consumed or what log sequence number they're up to. Okay, so now physically, if you wanted to scale that log out, you'd shard it into multiple partitions. And if you did that, then that is exactly the backend of Apache Kafka, where a log is a logical category of data or a topic, but physically a log lives in partitions that live on brokers and are fully replicated. As events occur, they're continually appended to one of the partitions log, and there is, a mechanism to maintain a fixed window of the log. Sometimes it is based on time, let's say retain a week worth of data, or it is based on size, maintain a terabyte or less. It is completely configurable. As I mentioned before, Kafka is a multi-subscriber system. So the same topic can be consumed by multiple, groups of consumers. So every consumer group gets a full copy of the data and are fully independent from each other. So every consumer group, it has a couple instances that could be deployed on several machines. And Kafka does the work of evenly distributing the partitions of the subscribed topic evenly amongst the consumer instances in a group. So to make sure that every partition in the subscribed topic is always consumed by exactly one consumer instance in the group. So the group in total can get all the data. And the nice thing is that if one of the consumer instances fail, then the other ones automatically rebalance to pick up the load of the failed consumer instance. And all of this happens under the cover. So, adding sort of horizontally, distributed subscribers to Kafka is operationally pretty cheap. Okay, so our Kafka adoption at LinkedIn sort of grew gradually over time. We started with, less important data like application log data, grew it to user activity log data, application metrics, and finally, all the database data also flows through Kafka at LinkedIn. Essentially, all the data sources are available centrally through Kafka. Initially, our two major subscribers of all the data were our relational data warehouse as well as Hadoop. But over time, a lot of, real-time applications emerged. And all they did was, tap into this central Kafka-based platform and get access to Kafka streams. What's really cool about this is that for any data source to be accessible company-wide, the investment involved was just a one-time integration with Kafka instead of the point-to-point integration with every system that needed access to that data source. And finally, with Kafka becoming sort of the central hub for all the data sources at LinkedIn, engineers found ways and means of processing it. Essentially, people wrote a lot of stream processing applications where Kafka is not only an input, but also the output of streaming data. So today, everything in LinkedIn is essentially a stream. These numbers are old, but Kafka, amounts to more than 1 trillion message writes per day at LinkedIn. And over time, Kafka got used at thousands of companies worldwide, from web companies like LinkedIn, Netflix, and Uber to larger sort of enterprises like Cisco, Goldman Sachs, and in these companies, Kafka is used in a variety of different ways. But if I were to give a few examples, I'd probably start with examples where data needs to be made available to real-time applications as well as some kind of batch system like Hadoop, right? Now, there are a lot of examples that use this sort of pattern of adopting Kafka, but monitoring is a particularly peculiar one. So, every company has applications that probably generate some kind of metrics. These are JMax metrics. You might also have operating system metrics from all your machines. And the problem is to make all of that available in some kind of, company-wide monitoring application. But really, monitoring is much more than just reactive analysis. What you also want to be able to do is spot week-over-week trends or have some kind of analytical workloads on that data. So typically, people end up pulling the same data into Hadoop, and that might happen through Flume or some other system. Now, the older, clunkier way of doing that is you end up with these two very different ways of pulling the same data into two systems. And the claim is that, this is pretty bad. Making these double writes is bad for several reasons. First is, this is operationally expensive. Having two different ways of loading the same data, you need to maintain two different tools, you need people to maintain it in different ways. And secondly, you no longer have the same view for all your data. So data that reaches your monitoring application might be slightly different from the way data gets loaded into Hadoop, especially when there are intermediate failures. There's just no way to know. So Foursquare, LinkedIn, and a bunch of other companies have moved over their monitoring data pipelines over to Kafka. Essentially, the way this works is you have these agents that collect data from every front-end machine and just directly send it to Kafka topics. Now your subscribers, monitoring application is just a real-time consumer of that feed of your monitoring data. And Hadoop has some kind of a Kafka HDFS connector that pulls all that data except at a very different rate. Now, same is true for log collection. Logs are a critical part of any system. They give you insight into how your system is doing. Virtually every process in a company generates logs in some form or the other. And the problem with logs happens to be the same. Typically logs need to go in, very different systems. It needs to go into a real-time search system like Elasticsearch or Solr these days. So developers and ops people can search through logs in real time. But it also needs to go into Hadoop so you can spot week over week trends. And this is the problem again, is you have these two very different tools of loading log data. And the advantage of, moving to Kafka is that it just helps integrate all these use cases where data needs to go to two different systems or several different systems that have very different consumption profiles, some that are real time, others that are near real time, some are batch. This pattern of copying data multiple times, what we've observed is it isn't limited to just monitoring data or log data. It just happens to be a very widespread problem in a company where applications evolve in a way where they end up writing application state multiple times to, create these denormalized views. Essentially, denormalization is just to make reads go faster. So I'm going to take an example to explain what I mean by denormalization. Assume that you had this stereotypical web app architecture to serve a LinkedIn profile. So when a user updates their profile, the web app writes those updates to a database. Now, this database could be anything. It could be HBase or Cassandra. It really doesn't matter. Now, this is great, but let's say you want to scale this with the growing number of users on your website, so you throw up some kind of cache. So now you add some custom logic in your web app to send the same write to two different places before, calling this profile update action complete. Now, this is also great, but let's say you want to add search feature to your website. So you throw up a third system, which is either Elasticsearch, Solr, or some other custom search system. And now your web app has to have custom logic to route it to yet a third place. And pretty soon you realize that this web app is slowing down. And the reason is because it has all this custom logic to route, the write to so many different places before it can synchronously confirm that the profile update is complete. So what you actually want is you want to decouple the writes or the updates to all these different denormalized views from the action of updating the LinkedIn, the user's profile. So that's where, Kafka comes in. Kafka is, not just scalable where, sharded topics can be consumed in parallel by these multiple subscribers. I think the key benefit is that it allows you to decouple the process of updating these various denormalized views from unblocking the action that generated that update. So to explain this, by introducing Kafka into the picture, your profile web app is pretty simple. All it does is it writes to the Kafka topic, waits for that write to be committed, and each different system merely acts as a Kafka consumer in the background and consume all that data and apply it at whatever rate it wants to. Okay, so once you've solved this problem of making data available very easily, company-wide through all the systems, like I mentioned, people find ways of processing it, and that's where stream processing comes in, is since Kafka is sort of the storage layer for streaming data, it is a very foundational building block for any kind of scalable real-time processing. In fact, stream processing just boils down to applying a set of functions on logs or streams or Kafka topics to generate more logs and streams. So taking a concrete example of what I mean here, let's assume that this is a very simplistic, credit card fraud protection example. Let's say that you have this stream or a log of credit card transactions where every message is some transaction made by some user somewhere. And let's say you write some code to consume it and be able to flag whether that transaction was a valid one or it needs to be put on hold for further verification. Now, that is great. You end up with these two different logs now from the original one, and you have some extra code that reads these on-hold transactions and then triggers some kind of verification steps. But let's say you wanted to extend this to flag some kind of a large-scale security breach, right? And let's assume that the metric used to do that is just the rate at which a large number of users are getting flagged in a certain period of time. So now you have some further processing that takes these on-hold transaction logs, windows it, and then creates a window topic. And the final step is to, take that window topic and count the number of users that were flagged in a certain time window and send an alert, right? Now, mechanics aside, if you look at this is nothing but stream processing. And what it is doing is it's just, some code that reads logs of data, process it in some way to generate more logs of data. So assume that these logs were actually Kafka topics. What it boils down to is using a Kafka consumer to subscribe to data, writing some custom code, and then using a producer to send that data, possibly repartitioned, to more Kafka topics. However, if you have enough of these ad hoc stream processing applications, then you probably want to consider using one of the several frameworks that allow you to express stream processing code, deploy it on machines, and operate it independently. Now, there are pros and cons of each one of these systems that I probably won't get into the details of here, but the thing to note here is that each one of these systems, they integrate very closely with Kafka to send stream data around or to store it. So, putting all of this together, this stream data platform, it really boils down to two things. One is having a storage layer for all the streaming data in your company. And second is, real-time applications that revolve around it to process all that data. And this real-time data or stream data, it really means different things for different companies. For retail, it could mean streams of orders and shipments. For finance, it could mean, streams of financial transactions. And for websites, it could mean streams of activity data from all the users. The point of having this sort of a stream data platform is to really make these disparate data sources available centrally in a uniform way, no matter how they are generated, so they're easily processable and accessible. A year ago, some of us who created Kafka, we left LinkedIn to create Confluent, and our mission is really to make this Kafka-based stream data platform a practical reality everywhere. And in terms of a product, it means a couple things. It means stream processing integration for Kafka. It means connectors for, making sure that streaming data flows to all the different systems using Kafka. A tool to monitor sort of end-to-end data flow so you can see how data flows through the various different systems that talk to Kafka. And a meaningful sort of schemas and metadata management story that works along with all these different tools. In fact, we have most of these things coming up in a release called Confluent Platform 2.0 in December. And finally, I want to leave you with the most important thought is that Confluent is hiring. Thank you. Do we have time for questions? Okay, great. Yeah, so the question is that they're using Kafka in their application or their company, and how do you actually figure out how many topics, Kafka can support, or how do you make sure you can size your clusters for a certain number of topics? The longer answer is actually on an excellent blog post written by Jun Rao, who's also my co-creator on Kafka and my co-founder. But the short answer is it's probably, Kafka is designed for number of topics in the range of about, tens of thousands. And the main bottleneck here is that we maintain the metadata about topics in Zookeeper. And beyond a point, maintaining that much metadata, Zookeeper becomes sort of the main bottleneck. So, I'd let you read the longer answer of, if I have n partitions and x topics, then how many brokers do I need? Or, how do I go about sizing my Kafka cluster on that blog post? You'd find it on confluent.io. Great. Okay. Can you go ahead?
What happens if, like, you lose a rack? How long does it take to rebuild that data? Data still available? Like, when it's become available?
So the question is about, reliability in Kafka, specifically if, as an example, if you lose a rack, then how long does it take for the cluster to rebuild itself? So I didn't talk a lot about, exactly how Kafka, replication works, but Kafka supports replication. So every write gets replicated on n brokers, where n is your replication factor. We're soon going to add rack-aware replica placement, so you will be able to configure, racks on your replicas. So you can make sure that if you lose a rack, that your entire partition is not offline. But the way it works is if you lose a particular replica, whether or not it's on a particular rack, Kafka, when you bring up the new broker, it starts with a particular ID. It automatically starts catching up with the leader of that partition. So Kafka follows a master-slave model for replication. And even if you lose a particular replica, the quorum shrinks and your writes can still continue if you've allowed for it in the producer. And when the failed replica comes back, it catches up with the leader. Once it catches up, it is added back into the quorum. So you can sort of expand it. Can you repeat that question? Throttle the... Yeah. Yeah, that's a great question. The question is, I mentioned that, replicas sort of catch up from the leader automatically. The question is, do you throttle replication? In this case, no, we don't throttle replication, but quotas, the quota support, which allows you to throttle this, data copy is being added in the next release of Kafka, which will be released, I think, sometime in November. What that will allow you to do is, as the cluster shrinks and expands, you tend to move data around to account for that, and that is actually the least important traffic in the cluster. That will be you will be able to throttle that traffic. Okay, what about DR? This is sort of a broad question, but Kafka has a DR story. You have this mirror maker tool, which allows you to copy data between data centers, and that is really asynchronous replication. So if we really don't, so far we don't recommend people do synchronous replication across data centers. Most often than not, that is actually not what people are looking for. What we have is a tool that allows you to do asynchronous replication. What we'd like to add, there is an ability that, if your DR side goes down, that it automatically syncs up the offsets, which it currently doesn't do. But that is how, we currently just support asynchronous DR. Any other? Oh. Are we out of time? Okay. Okay.
Where is Mateo? Okay. Next speaker is Mateo Merli from Yahoo. He will also be talking about a project built on top of Bookkeeper called CMS. Mateo is the tech lead for cloud messaging at Yahoo. And previously he worked on projects such as Sherpa and Tribble, also at Yahoo. And he's also a Bookkeeper committer. Ready?
Okay. Hi, everyone. So we'll be talking about what we built for our pub subsystem at Yahoo. And so I will go through a little bit of introduction of what cloud messaging system is, what it would provide, how we built it. I will go through how we built this, our service, and how we use Bookkeeper and what changes we did to Bookkeeper to improve our scalability and future developments. And yeah, okay, and future developments. So just a little bit of introduction. So what cloud messaging is? So we provide a PubSub service, which is a hosted system, and we use Bookkeeper as our storage. So I won't go through all the features of Bookkeeper, but basically we built on top of Bookkeeper because it provides the building block for consistency, durability, and it provides the very nice low-level guarantees. And it was a project that was started by Flavio at Yahoo Labs a few years ago, and so it's great that we can actually put to production the things that Yahoo Labs designed. So the main features that we have, that we provide to our customers are providing a hosted service. That is important because operating a system is very hard, and every application that needs to manage their own cluster, that would be very complicated. So we have features like authentication, self-service, quotas, and the main guarantees. So we try to have a very low latency service. That means that write latency needs to be in the order in the 2 milliseconds in the average publish latency, with 99% or 5 milliseconds. And we made a lot of changes, a lot of work to achieve that latencies. And the most important part is that this latency needs to hold even when there are like backlog draining scenarios and when consumers are not consuming, or where the data center cannot talk to each other. The other important part that we have worked is that we want to provide a very simple API with clear semantics, clear ordering guarantees, that people can start to use it very quickly and build their application. The service is there. You can just use the library and publish and receive messages. The dual replication is one of our key features in the sense that is a first level first class feature of the system, in that you can just configure the which regions do you want your data to be replicated into. So you publish on one region and you have consumers in any other region. You can just change this configuration on the fly. Also, we have load balancer. That means that we can add dynamically, if one broker is overloaded, we just shift loads, move topics to other brokers. And difference with other system, we also maintain the cursor position. That is important for us because otherwise application will need to store it somewhere. So you have a consumer, your consumer messages, you have to store your last position that you have acknowledged somewhere. So in our API, we support that and we store it in our system. So just to give an idea of the use cases that we target to support, we have identified 4 different classes of challenges for a messaging service. For example, there's a fan out use case. Fan out means you have rather low write rate, but you have many subscriptions. That means that for each message that comes in, you have to send 1,000 copies out, for example. Other use cases is that you want to have a single topic, a single producer, strong ordering, and you want high throughput and low latency. Other use cases are more like, I want up to possibly 1 million different topics, and each topic has its own ordering. And that exposes a whole class of issues and challenges to solve. And finally, funning, in which you have one logical topic, but here, since you have many producers producing to this one logical topic, which you can actually break it up in partitions to support unbounded incoming traffic. So how did we solve these issues, these use cases with a single system? So we've been thinking of going through all these use cases, and we've identified the minimal set of features that we want to expose and support. And so we started by defining a messaging model that we expose to our users. So messaging model, we have a topic, and to this topic, I can use the client library and create producers and consumers. So producers and consumers are ephemeral entities that exist only when they are connected to the brokers. So I create a producer, I connect to a topic, and I can send messages. If I'm a consumer, I have to subscribe to a topic, and I create a subscription, which is a durable resource. So I create a subscription on this topic. I can create many of them on the same topic, and this subscription can have different types for different use cases. For example, if I want to have, if I want to be the only consumer for this subscription, means that I want to receive all the messages for this subscription, then I create an exclusive subscription. If I want to load balance between multiple consumers, then I use a shared subscription type, which means that we'll do round robin across all the available consumers. And if I want to have ordering, but some kind of failover mechanism, I can just create a failover subscription in which one consumer will be actually receive messages, and the other consumer will just be in standby mode. So, given this model, we went on and decide what we need to provide as a client API, as a library to our users. So we basically want to wrap this concept of producer and consumer and not leak any other low-level detail like connections and so we provide simple and Java client library, and our client library basically is handling all this connection pooling, reconnection to the broker, to a different broker perhaps, and resending of messages without losing any ordering guarantees. And the other key feature that we embedded into this client library was that, and into the broker as a whole, as throughout the system, is that we want to have sync async version of all the operations. So our broker need to be scalable, so we need to handle thousands of producer and consumer connected to a single broker. So just to give a very quick idea of what the API looks like. So we want to have a high-level API in the sense that you can send a message. So you create a producer. Once you have a producer on a single topic, you can send messages and use this producer as long as you want. The send and send async basically are the same thing with the same guarantee that when the callback is triggered, that message was persisted in Bookkeeper. And the consumer is kind of the same. You can call receive or set a message listener, and once you get the message, you can just acknowledge the message. Acknowledge the message means that it signals back to the broker that you have consumed up to that point, and the broker will store that information. So if you reconnect, you will resume from that point. So just to expand on the first picture, we have different components. So as I said, we have a client library that our users embed in the application. We have brokers, which are stateless components. We keep our metadata in Zookeeper, and we store the data in bookies. We also have another component, which is Global Zookeeper, where we keep configuration data. So the client library works, by the way, by using first operation, we'll do some HTTP lookup to know which broker exactly needs to connect to. So that we go through some load balancer that will just run random broker. This broker will redirect to the appropriate broker. Then the broker itself basically keeps has a server. So once the producer connects to the broker, we use some binary protocol, some custom protocol for efficiency, and we just basically forward asynchronously the writes to the bookkeeper client and store it, and also cache it in the broker. So normally, all the data that consumer are getting is all coming from the cache in the broker, from memory. In the case where the broker restarts and then some other broker takes over, that happens automatically, and the broker will just read data from bookies and will cache it again if there are multiple readers for it. So just to go on other components. The replication is being done. So we have these global replicators that they act as consumers, as an internal consumer of the data. So if you configure that your data needs to be in this region A and B, then in region A, you will have a reader for region B. And that happens inside the broker itself. So this broker will take care of republishing the data into the other region. And finally, so the CMS system basically is a global service. You can connect from one region and consume from the other regions. The configuration, the provisioning configuration, and for example, the list of regions needs to be consistent across all these regions. So this is why we have added this global zookeeper component, which basically is, we use it as a globally consistent store. And the particularity is that since we have the quorum is spread across multiple data centers, even one data center being unreachable, that leave you can still change your provisioning configuration, which is typically the case that something that you want to do when some data center is down. And also we have changed the configuration on this Zookeeper quorum so that we also we keep reading stale data when the quorum is not available. So you will read, in case of network partitions, we favor to read stale configuration data versus not being able to read any config data. So to solve more high throughput cases, we also have added partition topics. So partition topics, basically, they work on top of normal cloud messaging topics, and the abstraction is provided in the client library. So the client library, when a topic is configured to be partitioned, let's say 32 partitions, then the client library will itself create internally. So you have the abstraction of having one single producer on a topic, on a logical topic, but internally it will create multiple producers on each partitions. And this partition can be reassigned to any available broker. So the API is effectively the same API that you have on a single topic, but is partitioned. And the way of choosing a partition for a message, so when you publish a message, we need to decide which partition to choose for this particular message. So there are different strategies. just a single producer can choose a single partition and keep using it, can do round robin, of course, losing ordering, or you can provide a key. So if you provide a key on the message, then it will be hashed on the key, and you will have per key ordering. On the receiver side, is more or less the same. You still have the abstraction of one single consumer for which you receive all the messages, but messages will be coming from different partitions. So since we presented before, we have different subscription type. We have exclusive subscription, we have shared, and failover subscription. The same semantic applies here. So if you have an exclusive subscription, means that you will be the exclusive consumer on all the partitions for this subscription. If you are shared, then you'll be a shared consumer on all the partitions. So you'll be getting messages in round robin from all the available partitions. While if you are in failover subscription type, the difference here is that the decision on who's being the master consumer on this partition is being taken at the partition level. And this has the advantage that we can exploit, that we can basically load balance the available consumer across the partition. So if you add more consumers, and your consumer will be taking over some of the partition traffic. And if one of your consumers goes down, then the other consumers will take over the partitions consuming. And this is done without any need to coordinate with Zookeeper across brokers or having the consumers to talk with Zookeeper. So let's say we store all the data and also the positions we store in Bookkeeper. And so we have developed a library on top of Bookkeeper client, which is called Manage Ledger, which is essentially, we just provide the abstraction of streams. As we said before, the Bookkeeper provide us basically a log segment, in the sense that you create this ledger, but you can write into it, but if you crash, you have to create a new one. So we have created this higher level abstraction, which represents an unlimited stream of messages, which is composed of a list of ledgers, essentially. So every once in a while, we create a new ledger. If we crash, we create a new ledger, and we add it to this list. So we keep track of the active list of ledgers. Also, for each consumer, we have an additional ledger, which we use to track his position. We just basically keep appending his position to this end of this ledger. In case of recovering, we read the last entry on this ledger to have the last acknowledged position. At this ledger, also, we cache the data. So we don't have to read from bookies, potentially from disk. And since we know the position for each consumer, we can delete data as soon as it has been consumed, or depending on the configuration, can be left around and expire automatically. So just to give a brief presentation on how a bookie works. So the good thing about Bookkeeper is that it has this, is designed to support multiple logical logs, ledgers, and to multiplex them. So a single bookie is able to serve efficiently many ledgers. And the way it does it is that the writes are going to separate physical devices. So you have a journal in which all the entries are committed before receiving an ACK, and then you have the ledger storage device, in which basically where the read will be coming from. So on this ledger storage device, the writes normally are done without f-syncing, and they are flashed periodically. When they're flashed, also you have an index for each ledger, because the writes are being interleaved basically on these entry logs. So since they are interleaved, then you need to know for each ledger, if I want to read entry 7 for this ledger, I need to know in which entry log, at which offset. So what we find out that if we want to increase the number of ledger per bookie, maintaining the same write latency guarantees, we have been finding that having a single index file separate for each ledger is a problem. It's a problem because when you flash it, you have to flash thousands potentially of index files that are scattered across all the disk. And the other issue is that since you have these many ledgers, that you make writes all over the disk, which on the ledger storage you want to keep HDD to have a larger storage, is that the writes, the non-synced writes on the ledger storage normally are just hitting the page cache, but if this disk is busy, they will wait on it. So that will impact the write latency. And also, this also happens when there are heavy reads. So if someone is draining backlog and is causing a big read traffic on the disk, that will impact the write latency. So to target these issues, we try to improve the ledger storage by adding some components in there. And so the first thing, we added a single database index. Instead of having an individual file for each ledger, we have some level DB in the index that is updated when the bookie storage is flushed. On top of it, we added in-memory write cache. So that means that the writes are going to the journal and are going into this write cache in memory, and the write is considered done and is acknowledged. If the bookie crashes, they will be replayed from the journal. So basically, this write cache is periodically flashed. Typically every minute we flash it, but we just swap it with the empty write cache. So the writes will never have to wait for the ledger storage to be writable, up to the write cache size, of course. So the other advantage of having the write cache is that since we do this periodically flash, we can reorder the entries on disk. So whenever we flash, we write entries from the same ledgers sequentially on disk. And the advantage of it is that typically we never read the data from Bookkeeper, but when we read, we want to drain backlog. When you want to drain backlog for a single topic, for a single ledger, you want to read all the entries sequentially. So if for each flash period we have all the entries sequentially stored on disk, we can take advantage of that, and we can add a read-ahead cache. So if you try to read entry 0, we internally, before you read all the entries, we actually read a few more entries from disk, so that for the same IOPS, we read more data. And yes, and the last thing that basically these offsets, this location index that we keep in the single level DB, this basically is only updated when we flash. So when we flash the write cache, we add all the entries into the entry log, we update the index, and we continue from there. So after having tuning for the hardware, like the journal device, the ledger storage device, we found that the latest obstacle on having like very low latency bookkeeper writes were caused by the JVM DC. So we tried to tune it, the JVM DC with all the possible flags, but there's no way to have it like a very low latency as it is. So we tried the hard way, which is we have to make it easier for the JVM to do its work, and that means that to reduce the number of allocations. And the biggest source in terms of allocation size is the payload. So if we can remove the payload from the JVM DC, from the JVM heap, then the DC has not to do nothing with it. So we've been working on basically adding we moved to NET4 and we have this pooled buffer with the ref count. So basically, through all the CMS broker to bookkeeper, we read from a NET socket, we get a direct buffer, which is coming from a pool. We'll pass it on to bookkeeper client without any copies, and bookkeeper client will write it on a new socket and we'll pass it on to the bookies. The bookie will do itself. We'll do the same thing. We'll get this direct buffer from a pool and we'll pass it on to the journal so that no copies are being done in all these passes. And this is all ref counted, which unfortunately in Java, it has to be explicit ref counting, which is kind of tricky, but it pays off in the sense that we can avoid a lot of work for GC. The next part is through all these, like we've been profiling and seeing, like if for each message how many allocations are being done, because the more allocation, the more time that GC has to spend to going through all the references and copying them over to the next gen and so on. So we went after all the easy low-hanging fruits. There were some, in some cases it was very easy to go around it. In some cases it was like more difficult. But basically, the key pattern here is that we try to pull all the objects. They're like whenever you add you have a collection of longs, for example, you have to change it to some primitive collections. There are some libraries that are doing that, but not concurrent libraries. So we've been adding concurrent hash map that work without allocations, or B3 instead of concurrent skip list to have an ordered concurrent map. So this is kind of like very, very long incremental work, but the upside effect of it is that we've been actually trying to have very low latency on bookie writes, independent of the number of ledgers per bookie. So we try to scale it at up to 50K ledgers per bookie, and with at the same write rate, the latency stays down at 1.8 or 6 milliseconds on a single bookie. We don't have this. I don't have it here. And the thing about the 1 point as offset is also that consider that we are doing like 1 millisecond group commit, so that the journal always we do around 1K fsync per second. So there is an average latency of like 0.5 milliseconds that is being added to the. But on the advantage for that is that we can do more writes per second. Size is 1K messages. So actually, we can do more writes per second on a single bookie, and with good latencies still. This was just to prove that we even like adding more ledgers doesn't affect the write latency. So just on the future, I will just go through very, very quickly. So one thing that we don't have currently is batching. So all these numbers basically are like for when you publish a message on CMS, basically it corresponds to an entry in Bookkeeper. And we find out that for many use cases, you want to be able to trade a little bit of latency for more throughput. Because if you can batch more entries into a single Bookkeeper entry, actually what we want to do is end-to-end batching, so that from the producer, you transparently batches more entries and just send one big entry to CMS broker that then just use one bigger Bookkeeper entry. the advantage is that we can reduce the CPU usage and the impact on DC, because if less CMS messages, less bookkeeper entries means less allocations, so lower impact of DC. And the other field that we want to also explore is that we want to reduce the durability guarantees. So right now we only offer high durability guarantees. That means that each message is stored in bookies and stored on disk and f-sync before return. That works great for consistency. If you want to have high durability and high consistency, you can also configure how many replicas you want to write into, but it can be costly. If you want to have like high throughput and you can afford to lose some time data when things go very badly, you might want to relax some durability guarantees to have a lower cost. It means if you, for example, if you skip the journal, you could still write data on multiple bookies. You take advantage that your data is replicated. But if you don't write it into the journal, then the I/O bottleneck can be removed, and at the expense that if both bookie crashes, then you can have holes in your ledger. It means that you might have read failures that you have to deal by skipping messages, for example. But yeah, everything has its pros and cons, and for different use cases. So now if you have any questions. Thank you. Okay. Okay.
So I think I understand the argument for the throughput performance dropping as you increase the number of ledgers per
Mm-hmm.
bookie.
So
Because I thought we had done that before. We introduced the
Mm-hmm.
component.
So what the specific?
Can you explain the argument? So why, as an increase in
Okay.
ledgers per bookie,
So yeah. So
performance dropping at the gradient?
yeah. So the main thing is that we were seeing that with more ledgers, basically you have all these. For example, if you have like 50,000 ledgers in a single bookie, you have 50,000 index files, one for each ledger. Now, if you have writes on all these ledgers, each time you flash, you have to basically f-sync each and every file. And these files are on different locations on the disk. They're flashed periodically, but when the flash happens, it will cause basically writes all over the disk. But this
Unless the number is so high that your cache is crashing, essentially. Right? So you're not able even to fill up a page, and you have to sync that all the time. And then it becomes really heavy, but the number has to be, the number needs to be really high.
But so for example, one thing is that you have the ledger cache, right? Ledger cache basically has a fixed size. So you configure the number of maximum open files in your ledger cache. So once you exceed that, then basically the ledger cache is so the problem is even worse, because you have also the book ETC that happens and is polluting the ledger cache. So if your number of ledgers exceed the ledger cache, then each write potentially incurs in opening a ledger index that has been evicted from this cache. So you can increase your ledger cache size, but also the ledger cache size means that you need to have potentially one FD because the file is mapped, so you need an FD to have an entry in the write cache on the ledger cache. So you need to have so you can increase the ledger cache size, but you still you cannot have it that bigger because you have you need to have one FD per each ledger in the write cache. So for example, if you run with 20,000 ledger in the ledger cache, the moment that the bookies have more than 24K ledgers, then the latency will be probably be high because every write we try to open a new one. So we could increase it to 40K, but then you still have a ceiling there. Okay. Mm-hmm.
Are your improvements already in the
not really. That was the plan. We've been talking. So the question is that is if these improvements are in the open source branch, and the answer is that they should be, but they are not yet. So we want to push it back to the open source for many reasons, and but that takes. Okay. 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 So the question is, how do we cope with the different number of also or so I mean the number of producer well, so if we have, of course, like for a single topic, you have some upper bound, right? If a single topic if it is not partitioned, it will be served by a single broker. So you have the single broker CPU, memory, or network limit that you can that you cannot go over. If you reach this limit, you probably need to shard it in a partition topic. For the number of producers, we tried with many producers. Maintaining the same rate is not an issue. Basically the broker is handling all these producers asynchronously and is able to sustain thousands of topics, tens of thousands of topics in the same broker with several producers. For a number of consumers, the key point is that if they are on different subscription, means that if you have multiple subscription on the same topic, then multiple copies of the data need to go out. So at that point, the first bottleneck will become the network in the broker itself, which you can still tackle this issue by having partitions, by partitioning the topic, so that consumer will consume from multiple partitions, and a single broker will have less amount of traffic. Okay.
Can you say in production the number of ledgers you're running per book?
In production, I think per bookie, I think we reached tens of thousands, yeah. And so the idea is that if there are like use cases in which you want to create many topics, with each topic has a very low rate, right? But you still you need to have multiple ledgers for it. So the write rate actually is not that different, right? From a single topic that with high rate or many topics, but so the same book will have many ledgers with overall roughly the same rate. So before using Bookkeeper, we were trying to use some metadata store, but wanted to use Sherpa at Yahoo, but then we say, okay, if you use Sherpa, then Sherpa cannot use cloud messaging. So we say, okay, we cannot use Sherpa. So we could have used some other data store, like HBase. There was some idea of using HBase, but then you say, well, when you ask people that you want to use another that database just for it, they will look at you as you are crazy. So we say what we have at hand. So we say we have a log that you can do very fast writes. And how can we do it? So we just figured out that we could do that by just appending and using as a basically as a checkpoint for the consumer position. Yeah, it's pure pending and it's not overriding. So every once in a while, we just create a new ledger and delete the old one, and that's it. So it's fast, but in a way also it's a bit more expensive because you need to have a ledger with all these metadata to just for the consumer. Yeah. Okay. Thank you. And yeah, and by the way, we are also hiring. So.